Okay, on to the last long question. That's going to be worth 10 points. If you're really slow at these long ones, you might want to work backwards from the test questions and do the short ones first to sort of warm up. But, I can do these pretty quickly, so I like doing them in order. So let's see if we can do this one in my 20-minute limit. 23 is what they suggest, but like I said, I like taking a nap at the end of the exam. So turn my little timer over and start that thing going. Okay, here we go. Question 3. Sulfur trioxide. Yeah, that's a popular one in AP questions too. Is commercially produced, massive scale, produced as a byproduct. Yeah, air pollutant. Okay, good. That's true. In fact, it's when they try and get rid of the SO3 by having it dissolve in water, but that's another story. Okay, grains of sand are falling. On the box below, complete one of the valid Lewis dot diagrams for SO3 molecule. So we only need to do one, because there's a number of possibilities for this. Be sure to include all the valence electrons, including lone pairs. Okay, well, we got to get valence electrons. Valence electrons, let's see, we've got sulfur. That's right underneath oxygen 6, and you should know by now oxygen has 6 valence electrons. Look at the periodic table if you have to, but come on, we've done these often enough. So we've got 3 of them. So this is 18 plus 6, 24 valence electrons, a pretty common one. I better double check on this. Yeah, 4 times 6, this is going to be it. So we have to deal with 24 valence electrons. They give us the shape here, which is very nice. Sulfur is at the center. Usually the less electronegative substance is at the center. And we're going to put in 3 bonds. I've got my 24 minus 6. That leaves me 18 left behind. I'm going to double check that subtraction. Yeah. Now, I'm going to next complete the octets for the surrounding atoms. So I'm going to do 6, 6, 6, and that's all my valence electrons. They're all used up. But we know something's amiss, and because our central atom doesn't have the minimum octet. Aluminum could, boron could, but not sulfur. If this was boron, you'd close the book. Same thing for aluminum. Those are the 2 exceptions. Sulfur isn't one of them. It's going to need an octet. So I'm going to choose a pair of electrons, cross them out. That's all I have to do, and move them over. That's it, and we're set. Now, you might look at formal charges on this and realize that the formal charges aren't ideal, and that really 2 double bonds here would be better. And if you did make a second set of double bonds, or even a third set of double bonds, by crossing out a pair of electrons from each oxygen to make a it'd be fine. Sulfur can handle up to 10 valence electrons very, very easily. All those would be correct. I'm going to go with this simpler one, even though it doesn't have the preferred formal charge, just because they didn't ask anything about that. So this bond resonates all the way around, so we'd expect to have equal bond lengths on this. But okay, wait a second. I've done it including the lone pairs. I've got the lone pairs here. I've crossed this one out. We're set on this. We've taken care of all of 18 electrons. So let's move on. Predict the shape of the SO3 molecule. You know your shapes. We've got 3 pairs of electrons, 3 domains. One domain, remember, double bond is considered to be just one thing because still it really occupies that space. That pi bond is above and below. 2, 3. 3 things in space is trigonal planar. Trigonal planar is the name. And predict the shape that you completed. Trigonal planar, they didn't ask for the angles, which would be 120 degrees, do they? No, predict the shape, trigonal planar. Okay, that's it. That's easy. We're moving along. Hey, we don't have time left over on this one. Okay, let's keep going. Under some conditions, the SO3 decomposes to make sulfur dioxide and oxygen as presented in the equation below. Okay, exothermic reaction. No. It's a positive sign. It's endothermic. Under what temperature conditions will the reaction be thermodynamically favored? High temperatures, low temperatures, all temperatures, or no temperatures? Justify your answer in terms of the change in enthalpy and change in entropy. Okay, delta H equals plus, not thermofavored. Delta S, that's our change in entropy. Let's see, 2 moles of gas, 3 moles of gas. More moles of gas. We've got a greater distribution of matter. That's an increase in delta S. Increase in delta S is thermofavored. Okay, we've talked about change in entropy and change in enthalpy. Gives free energy is delta H minus T delta S. Increase in T magnifies delta S, high temps. Favor. So this is favored at high temperature. That's probably 1 point. And we gave the reason because of the increase in entropy. Okay, plenty of time left. I didn't use paragraphs or anything else. I just identified and said delta S, thermofavored, and gave the equation. And when you increase temperature, we're set. Okay, so I'm happy with that. On to D. Answer the following. Okay, a chemist fills a rigid SO3 at a certain temperature until so keep the temperature the same until the pressure of SO3 in the container is 0.83. The SO3 decomposes, so they put this stuff in and decomposes in these gases. Okay, he starts with some SO3, nothing else, and the SO3 decomposes and makes SO2 and O2. Answer the following questions based on the graph. Draw an X on the timeline to show when the system has first reached equilibrium. At equilibrium, we don't have any changes. There's no macroscopic changes. The pressure will be the same. So here, when the curve flattens out, that means that things are pretty much the same. So draw an X on the time axis. Here's our time axis. Here's where things level off. Done. Describe the change that was made to the system at T1. Okay, here's T1. Things are the same, things are the same, things are the same. Here's the change. Look at this. A rise in SO2. Okay, they must have dumped some SO2 in because this went up very, very quickly. And these things gradually adjusted afterwards. So the real change made here, the only thing that's changing right here at T1 is SO2. I mean, the only way we could have an increase in charge is SO2 was added. I don't think you even need to be a chemistry student to figure that out. It's just a matter of looking at the graph. Okay, that's taken care of. We haven't even used up 15 minutes and we're at D, the end of D. After the change was made, the partial pressure of SO3 increased while the partial pressure of O2 decreased. Explain this observation. Okay, I'm going to write the equation. SO3, all gases, changing to SO2 plus O2. So, increase in SO2 caused a reaction to go backwards. So SO3 went backwards, and SO2 plus O2, this is consumed, and this is increased. I'll use parentheses to indicate pressure. So increase in SO2, disturbed equilibrium, because this was at equilibrium, and cause the reaction to shift backwards. Now, explain, I might end up indicating that Q became, because we had more products, greater than K. And therefore the reaction went backwards. When they say explain, you want to do a little bit more. And if I had more space here, I would have done it, but I've got it here. When they read it, they'll see Q is greater than K, then that's the explanation, because we have increased the SO2. That caused the reaction to move backwards, and we've explained it. Okay, that's it. We'll see that. You'll see the critical things, Q greater than Q, reaction goes backwards. Here, I'll put an equilibrium arrow there. Here's 1, here's 2. That explains it. Oh, okay, no, I still got 15 minutes left. I still have time left on my old sand timer. Look at that. Whoa. Neat. I haven't had to use my calculator yet either on question number 3. So anyway, let's see what's left. Okay, use the information above. Now that would be on the graph that we had. Again, this would be set up so that these two pages would be opposing one another, so that we could look at this graph. Write the expression for the equilibrium constant for the reaction. Well, we know what the reaction is products over reactants. And look, they said Kp. Okay, I know what they're looking for here. Kp is pressure, it's not concentration. So we don't use concentration units. And it's going to be products. And let me get the balanced reaction on this thing. In fact, that balanced reaction was given way back here. We have 2 SO3s making SO2 plus O2, and we have to have a coefficient of 2 here. Coefficients are critical. Products, SO2. Now, this is gas pressure. You don't put brackets. Bracket stands for molar concentration. So we have to use parentheses. In fact, that's the trap that's going to mess a lot of people up on this. Well, that's good. They're going to mess up. I'm not going to. Neither are you. Okay. Other product, O2, in parentheses. That says the pressure in atmospheres. And then our SO3, don't forget that's got to be squared too because of the coefficient. Okay, Kp. Had this been a Kc, we would have used brackets. Okay, determine the Kp for the reaction. So we're going to have to know these pressures and plug them in. Well, we've got the equation. Now, I've got this equation wrong. Plugging them in, if you put the right numbers in and followed it, they wouldn't double penalize you. But we've got to look over here and find an equilibrium situation. You could use it here, 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 or here. Either one of these spots. Let me use this one right here. This one has a nice 0.5 for the SO3. So I see my SO3 is going to be, well, that's my reactant. SO3 is going to be 0.50. And I'm double checking. Yep, that's SO3 squared. Now I'm going to have to look for my SO2 at the same equilibrium. SO2 between 0.3 and 0.35. I'm going to guess 0.34. 0.34 squared. And that's an estimate. We could have used the ones here at equilibrium, but I prefer these because they're closer to the numbers. Now don't mess up as badly. Now all I have to do is find out my O2. Oops. And I'm just used up. Oh no, I still have a few seconds left in my 15-minute timer. Let me see if I can do it. Let me look at the graph. O2, a little bit of estimating on a graph. 0.1, 0.2, 0.15, 0.16, 0.17. I can make it 1.7. 0.17. I've used up 15 minutes. About 5-minute timer left. And just have to do this calculation. Calculator time. Okay. Turn my calculator on. And just put the right numbers in. 0.34. I have a squared button, which is fun. Times 0.17. Now let me just put an enter in. I could do a divide by 0.5 squared, but then I'm going to divide by 0.5 squared. All right, let's see what we get. Okay, I get a Kp is equal to 0.07. I only had 2 significant digits, so I'm going to go 9. No units. Had this been a rate law, we would have to have units, but there are no units used for equilibrium expressions. It's the only case where we don't end up using units, but this is based on the pressure. So they know the pressure was done originally in atmospheres. Let me check. That's less than 1. That means that we end up having fewer products than we end up having reactants. And here, look, here, we still have more SO3. We didn't get that much in terms of our products that are made. So having a Kp less than 1 is what I would have expecting. So I think this answer might be right. I'm going to double check. I have a little bit of time. My SO3, about half. Yeah, my SO2, a little bit more than 0.34. Yeah, squared. That's it. I think we're done. Oh, let's see. Is there anything more? Come on. No, that's it. That's 3. That was the last long one. Holy cow. And we got time left over. If you really did have time left over when you're done with the exam, you can go back and check these numbers. But I think we got it. We made our answers. And hey, that's it. Question number 3 taken care of. And we only have now the real short questions, the 4, 5, 6, 7. That's it. Well, let's close this one down.